This presentation lays out the Urban Stream Project's Geophysical Stream Surveys Protocol as it stands right now. And I'm recording this on April 16th, 2024. We've been through several rounds of refinement of this protocol, but it may still undergo changes. So if you're watching this, later on, then just take note that things may have changed or been optimized or something like that. And I probably won't re-record the whole presentation, but instead watch this and then look for any updates, just in, how the data sheets have been written or anything like that. The important thing is that, the majority of what's in this presentation is going to remain as it is. And so I think it's all set. Okay, so what am I going to cover in this presentation? First, I'm going to provide a reminder of what the essential project goals are as to why we're doing field surveys in the first place. Then I'll go through some background, essential geophysical concepts. Obviously, I can't cover like all of fluvial geomorphology and things like that, but I just want to highlight a few points. For those of you who are coming out in the field with us, you'll get more training as we go along and be learning how to read the landscape and understand how a river functions. Then we're going to go through the general site assessment procedure. It's fairly detailed, but it's very important. One of the lessons that I've got just from making this assessment procedure is that there's actually a lot of really useful qualitative you can get just answering yes and no questions. Just some basic information can provide useful variables for our project. Then we're going to go through where transects get located at a site. We'll talk about how we collect data in terms of, quote, surveying those transects. We'll then talk about riverbed sediment characterization and photo documentation. So let me start off by talking a little bit about the study purpose. Why are we doing this field work? Like, obviously, you don't just go out and collect data without knowing exactly how you're going to use it. And in this case, we do know that. The overall goal of the field data collection campaign is to observe and quantify a wide diversity of bay area, stream, geophysical conditions. So there's a lot of different kinds of streams out there, and maybe we can't get every nuance of every kind of stream that's out there, but the more that we can collect data about them, the better we can understand the totality of what's there and come up with specific strategies for managing different problems in different conditions. At a minimum, what I'm going to call the first year field surveys, which is the main 8-month campaign that we're going to be starting very shortly, that survey has to obtain variables from each site suitable to achieve the following things. First, for creating a typology of various stream reaches using cluster analysis. Second, for training machine learning models to predict the stream type of every 200 stream interval in the Bay Area. You have to take the whole network of streams throughout the Bay Area, 9 counties, and you break it up into 200-meter slices. Then we want to be able to predict what is the stream type in all those locations, even though we can't go to all those locations and measure them. Finally, there's a third goal that we want to achieve as much as possible, but we're not committed to doing this. Like, we don't have the resources, time, it just simply may not be possible to do this everywhere, or even possibly at a majority of the sites. In fact, we didn't even propose that we would do this from the outset, but it's an opportunity that we want to take advantage of. And that is that from the way we collect data, we want to try to have the best chance possible to be able to make simplified topographic models or digital elevation models of each stream type. Now, I want to differentiate first year from second year field surveys. Second year surveys will go back to sites and do very detailed surveys of a small number of sites. So, I'm hoping we can get 250 sites visited in the main campaign here. And then maybe in the second campaign, we just do like 10 sites in great detail. That's why trying, where we can, collecting cross-sectional data, but in ways that have really good georeferencing is wonderful when that's possible. So what do I mean by classifying? Well, when you go to a site, you can take all the data and then you can turn it into site averaged variables like, site scale, slope, width, riverbed height, bankful height, active width height, valley height, entrenchment ratio, sinuosity, these site averaged variables. And for each variable, there's a mean, there's a standard deviation, there's a coefficient of variation. Because they're measured at many cross sections. So you take those variables and you use a cluster dendrogram and you get a result like this. So each vertical stick here is a site. And this is from the statewide survey that we did a few years ago from one of the regions. So each is a stick. And then any two sites that are, have very similar attributes for their variables are plotted next to each other. And the higher up you go for connectivity, then the more different they become. The blue boxes show where a distinction was made in types at that level of variation. So each box is a type. I'm not going to go into all the details of this. I'm just trying to illustrate so you understand the goal here. The goal is to take all of the sites throughout the 9-county barrier region, collect variables where we get those variables at all sites, and then using those variables, create a cluster-based hierarchical dendrogram that gives us types. There's other details, a variety of ways of doing this. I'm just trying to give you a flavor of how that goal works and why we need to have the field survey. The other goal is about the machine learning model. This is an example on the right of like after we visited a section of coastal California for the statewide project, with the training data we had, we can then predict every section of stream in 200-meter intervals. Each color is a different stream type in that particular region. So the data we collect in the field goes to the cluster analysis. The cluster analysis spits out cluster types or names or whatever you want to call them. They're type 1, type 2, type 3, or maybe you call them confined gravel bed, river with boulders. It doesn't really matter. That becomes your training data. The labels, the stream type labels are the training data. The training uses a machine learning model where there are predictor rasters. The predictor rasters are other sources of data that are widely available at coarser resolution than the field data, and you can then make predictions. Again, I'm just giving you a flavor of why we're doing this and what kind of data we need. So when I talk about a year one field site survey, what I mean is that we're going to go to cross sections and we're going to measure their shape among other variables that are measured there. But I want to focus on the topographic information. In an ideal scenario, we would collect that information, georeference to real world coordinates, and where each cross section is referenced to each other in those real world coordinates. If that's not feasible, then you go down to the next level, which is collecting them all in coordinates that are not tied to real world coordinates, but are tied to a local coordinate system, but they're still all referenced to each other. If that isn't possible, then the goal is to just collect it where each transect is known for its cross section, and then its height relative to all the other heights are measured, and the distances between transects are known, but you wouldn't have this bend anymore. You wouldn't be able to get the sort of like the lateral sinuosity of a river. You would just have each transect independently in like what we would call a streamwise coordinate system. In year two, in year two, we'll be doing full digital elevation model surveys. And those surveys will go into this other procedure on the right. Now, it is possible that the year one data can also be used in these surveys because of other research that my lab group and Professor Belize Lane's lab group at Utah State University has been doing. All of the georeferenced, data in like a full three-dimensional coordinate system could also be used here. The cross-section based data collected without that full coordinate system has the potential to be used, although I'd prefer not to do it that way if we don't need to. Anyway, this slide is just emphasizing that opportunistically, where it's cost effective, where it's not too time consuming, we'll go for this. But I want to be clear, it is not worth the resources. It is not worth the time to commit to doing this at all sites in highest possible resolution, because we don't need that for the main purpose of what this year one survey is, which is the cluster analysis and machine learning prediction. Okay, well, if you really are still not satisfied, like, oh, but what are the goals of this project? What are we trying to do? I have these two lovely schematics for you. They show the entire structure of the project. I am not going through this right now, but you can see that this is only half of it. And out of this half, what I'm talking about today relates to one box, the observed 260 stream sites. I don't know if we're going to get 260. Maybe we'll get more, probably get less. But basically, it takes an enormous amount of work to get the field data, and then all the rest. Well, not all the rest, because there's other field surveys and things too. But a lot of this then is done from the office desk, so to speak. But anyway, this is half of it, the contemporary analysis, and then this is the second half of our project scope, which is the future scenarios, forecasting conditions from 2030. Oh, I have a typo. It should be 2030 to 2070, not 3070, but that's okay. All the rest are correct. Anyway, we do know exactly what we're doing, why we're doing it, where it's all going. So let's just talk about now, what is the data that feeds the goal of getting us to the stream archetypes box and the contemporary machine learning model box? Like, that's why we're getting these observations. Okay, so now we're up to the part of the presentation where I want to talk about some background geophysical concepts. Yeah, and then we have the rest. Okay. Now, one of the things that's super duper tricky is there's just such a wide variety of streams in the Bay Area. We're talking about boulder, bedrock, step pool systems. We're talking about vegetation covered small little creeks. We're talking about wide riffle pool rivers. We're talking about totally concrete channels, or just like, here's one with just gabion structures, but then a boulder strewn bed. Here I am in a creek, not in the Bay Area, I guess, but still like deeply incised, and then a flat channel bed. Or on the right, you get to some of the larger streams. They're going to have these, big levees. Well, not a levee, I should say, but banks onto high terraces with maybe an inset floodplain, if at all, and then the channel bed. In any case, this isn't even the full diversity of what we're going to see. Now, why am I bringing this to your attention? Because traditionally, when we do river classification, we need a set of variables that we can measure at all sites. And there are certain variables that geomorphologists have fabricated, socially constructed, that as if they exist everywhere, and then they create a uniformity of data collection. But really, those cannot exist across everything from artificial to natural settings. So there's going to be some significant deviations if you're like a idealistic geomorphologist. You're like, but the textbook says something or other. Well, that textbook doesn't work when you get to the scope of what we're trying to do. So we have to have a procedure that's more flexible and diverse and viable for this setting. Okay, so when we think about a river corridor, we can think about it for three planes. We have, when you look from the top down, the planform view. If you look from the side, we have the profile view in green. And then if you look upstream to downstream, you have the cross-sectional view. Generally, we'll be collecting data from all of those different viewpoints in the field data collection. Let me give you some definitions about things in rivers. In drier climates, we have what we call an active channel. So many times in the dry season, half of a riverbed might be dry or all might be dry, and you can see where the riverbed sediments, which tend to be coarser than the bank sediments, where those are present. They will often not only be present on the bed, but they may even be present on the banks. So where you see active riverbed sediment, which is usually coarse again. So, if you're in like a cobble bedded river, that could be gravel and cobble. At some point, you'll see a transition to maybe mud and grass. And it's yes, mud is still sediment, but that's no longer likely to be the active channel because it's not the riverbed sediments. In theory, the entire channel that is active constitutes that at and below bankful discharge. However, in practice in California, that often isn't the case. For example, if the river is incising, there may be no depositional setting that would constitute a floodplain for which to delineate, quote, bankful discharge. So in an incising river, you can still delineate active channel, but it isn't necessarily the bankful channel. So the bankful stage is the elevation of the water surface when rising water completely fills the active channel and first begins to spill onto the local floodplain. There are very specific conditions in which you can observe bankful. I mean, it assumes a long-term equilibrium between sediment erosion and deposition, the hydrologic regime, flood disturbance regime in terms of disturbance followed by recovery. You can't have long-term incision. You can't have long-term deposition. Like you have to have a generally balance condition over time. And many streams, especially where you have intensive land use from agriculture, deforestation, wildfires, urbanization, like all of these things can eliminate correct bankful indicators. The floodplain is a relatively flat valley floor surface that has been constructed during the present hydrologic regime by the natural processes of point bar deposition, lateral channel migration, and vertical accretion of sediments that have been transported beyond the active channel boundaries during periods of flood. So generally, when this sediment leaves the channel from overbank deposition, it's finer. It's like mud and sand, as opposed to the riverbed, but like if it's composed of sand and gravel or gravel and cobble. And so floodplain is a flat depositional surface generally. Not all rivers have them. So, but you need to pretty much have some kind of floodplain or depositional feature in order to identify bankful. We're also going to note that the left bank is like, as you look downstream, your left hand in the downstream direction, that's the left side of the river. And as you face downstream, the right side, the right bank, we call that river left and river right. And that's the convention we use. Okay, so let's take some illustration of these definitions. And over the course of this presentation, I'll show you many cross sections with different views. So we can define an active channel as the length of the riverbed, and it can also include the banks, as long as you see the same bed material along the banks, then that is active channel. In California, we often have depositional environments where you have multiple threads of channel and active sediment is spread over quite a large area. And so you can see the history of floods that are there and help to delineate where that active channel is, even in a very wide channel with many smaller threads when the river is low in the summertime when we're doing field work. The bankful stage is what's filling that up to the level of the flat floodplain. So if you have an asymmetric channel and you have another flat surface at a higher elevation, you have to be able to determine which is the floodplain, and then anything higher than that is a terrace. So here we have a floodplain. We have a low terrace that's visible on both sides of the river. And then we have a high terrace only on the right side of the river. So this is a good reminder that the left and right side of the river quarter, they don't have to have the same features on them. They can be different. We can talk about the valley floor, like what is called here a fluvial plain. I would call that the valley floor myself. Like the valley floor consists of terraces, floodplain, and the channel. Well, I would include the channel in the valley floor, of course. Well, no, let me take that back. I would include it in the valley, but the valley floor would be everything other than the channel. At the far edge, there may be a valley edge there, but we could also talk about the valley edge at the floodplain channel boundary. This bank top could also be considered a valley edge as well. Okay, so active channel and bankful channel should be the same thing, as I've already said, but as an example, in an incising river, it's not the same thing. Or what if the banks are cement or gabion structures, or there's fences there? Like, you're not going to see bankful indicators in many of the streams in the Bay Area because it violates the geomorphic theory about the equilibrium and those sorts of things. So we cannot count in this project on this sort of fairy tale of bankful everywhere and then using that as a yardstick, so to speak, for everything else that we do. We have to take what nature gives us. We follow nature under all circumstances and observe what we can interpret and confidently see. Now here's a photo. Now this is like an East Coast photo, but still it gives you a feel. So in this case, what I'm looking at when I interpret this is you see where the water is. For this project, we don't care about water for this field survey. The water is deceptive. Don't let it fool you. In this case, though, at a minimum, it's telling us that there's an inset base flow channel in here. I wouldn't, like, where the water is on any given day doesn't mean anything. What you're looking for is the geometric slope breaks. And I'll come back to this photo later in the presentation and show those. But the Thawag is shown here in the middle. It's the deepest or lowest elevation location as you go along the river. You're going to have, in this case, like an incised riverbed with a left and right toe. You have the top of the incised base flow channel left and right. Did I say riverbed before? I meant the base flow channel here. The base flow channel left and right toe, the left and right base flow channel top. Then you have the actual riverbed. So the active channel is this whole line, and presumably they've pushed the leaves out of the way and confirmed that there is active sediment transporting along these banks. But I would differentiate the riverbed toe at the slope break over here and over here, and then the active channel top, which in this case is being interpreted as a bankful stage. So you could call this the left and right bankful top. And then farther out, then you have the floodplain on the right, and then the floodplain transitions right to the hillside. So there's the outer valley edge. On the left side, there's a terrace, and then I can't see what's past that. In terms of the Thawag, I mentioned that the Thawag is the path of greatest depth down the river. Now, if the riverbed is not undulating, then the Thawag should just be the bisector of the channel. I would just go straight down. But if there are undulations, which could be in more of this, like what we call an alternate bar formation, or this is sort of gently sinuous, or it could be with a really sinuous river. Typically, what you'll see is you'll very clearly see a pool, downstream and upstream, and then you're not really sure. And so what I would say is find the deepest point in one pool, find the deepest point in the other pool, and then kind of like walk a path to connect those. You don't want to like go straight and then like suddenly cross the channel as a jagged line, like a lightning bolt, and then come over. You want to kind of continuously transition back and forth across the channel or wherever there is. I also want to point out that the intention here is primarily following the main landform of a pool riffle undulation. You may be on a riffle and there's a boulder sticking out, and so there's a local scour hole, what we call horseshoe scour, or just local scour around a boulder. Um, now, that is technically the deepest part of the channel, but if it's highly localized and it's not following a clear continuous path, I wouldn't I'd have to you'd have to really think through, like, can you effectively transition into that hole and then back out to continue down? Because it's if you do that and you sort of ruin the representation of a riffle, then you're missing that the landform is a riffle. It's like the landform is a riffle that happens to have a scour hole off on the side. The main point is to follow the landform of the river, not every large bed element, high or low, that's like on top of that. That's my professional opinion anyway of how I think we should do it. Okay, so I have reminded you of the goals, and now I've covered the background geophysical concepts. Now we're going to move into the general site assessment procedure. First of all, I want to talk about the site location. So I'm going to assume, for the purpose of this protocol, I'm not telling you how to find sites and how to determine if those sites are, how to get to them and things like that. But I'm going to say you're ready to go out in the field, and all sites should already have been stored as a KML file that you can import into your personal Google Maps as a saved map. You should do this before going into the field so you can view the sites, this should say sites, on your phone to get to those sites. So what am I talking about? So on your smartphone, you can download the Google Maps app. And if you're logged into your Google account while you're using that app, then you have something called My Places or My Maps. And you click in there, and then you can import a file. Generally, what I do is I do that on a computer. I go to maps.google.com, and I have the KML file of either all the sites for the whole project or just for a particular day. And I save them, or import them into Google Maps, save them with some sort of name, like, oh, okay, today's date, and these are the places I'm going to today. And then you can see them. So I think I'll do a quick demonstration of this. So if I go to maps, here's I'm logged, like on the right, I can see my picture, so I know I'm logged in. And then if I click on the saved button, and then I click on maps, I could do open mind maps, but I already have a bunch of maps. So like last week we went to Stebbins Cold Canyon. So if I zoom out, I can see, like, okay, compared to being in Davis, we just drove west, and you can see these two dots. One is blue and one is green. And so we can get to this parking area and then walk. Now, here's the key thing. You need to load this map while you have cellular service and keep that in your file, because once you lose cellular connection, if Google like restarts or resets or whatever, you lose it. So once I'm on my phone, like I don't switch and go to other things. I just keep these maps open. You can still zoom in and out. And then you can see, if I zoom in on a site, it has the whole 200-meter interval that is the potential study site, and it has a dot. And if I click on it, well, it's got basically all of the data from that spot. So there's quite a lot of information that's there. What I'm not seeing right now is the name of the river, but it does have the name of the site. So from our project, this is SAC 07_02. Like that's the site ID. But like you'd already want to know, okay, this is Cold Creek because it's located in Stebbins Cold Canyon or something. And so by having this preloaded, we could then hike along the trail to get to the site. So that's why I'm including this in the field protocol. I'm not telling you how you get these sites, but on any given day, like you should know how to drive to the parking area near a site, what your permissions are for accessing the site, any rules in the site area, and then have it on your phone. So like as you're walking along the trail, you know where the site begins and ends and where the midpoint is. Okay, so each site point is the midpoint of a 200-meter stream interval. You probably won't be surveying 200 meters unless that's determined from your site length in the later step. When you arrive at the site, you can choose, based on recon and physical indicators, which part of this 200 meters is the best for you to survey. If you had a dramatic change in conditions for a third of the site, then use the main part of the site. Don't do like half in some weird thing and half out or whatever. But on the other hand, if the site does require you to use the full 200 meters, then you use the full 200 meters. But I believe at most sites, it's going to be significantly longer. Like if it's a 3-meter wide channel, you're only going to go 45 meters long or something like that. So you have some flexibility, and I'll talk more about where you'd start your site and things like that. Okay, so for the general site assessment, what are we doing? So let me list the steps and then I'll explain what each one means. You arrive at the site location. Okay, that's fine. You write down the date, the site ID, the name of the stream, the crew members, just their initials, GP, KR, whatever, and then the name of the nearest urgent care facility. Now, I would recommend that you should already pre-populate this, before you go out, or like while you're driving. Somebody should have that data sheet and be getting all this information from their phone, particularly the nearest urgent care facility. I would just determine that on the way, but it's kind of up to you. Once you get to the site, the first thing you want to do is reconnaissance. Go to the midpoint, go to the upstream, go to the downstream, like try to figure out what is the safety at the site and have a conversation. Do we need to wear life jackets because it's really deep? Do we need to wear life jackets because there's big boulders and I don't want to break my ribs? Do I need a helmet? What do we, just is there poison oak? Anything like that. Look at the accessibility of the stream corridor. Can we walk along the riverbed? Can I walk on the banks? Is it incised? Can I walk on the top? Do I have to worry about falling over the cliff or something? You should also think about what type of surveying equipment is viable. We have 3 main instruments available: the RTK GPS, the total station, and the auto level. Every site is likely to be surveyable with the auto level. Like if you're in doubt, if it looks like it's going to take too long, just use the auto level. The auto level, it's been used for decades in geomorphology. It works. It gives us the data we need. It doesn't take a whole lot of effort. You just write everything on the data sheet, and that's great. If the sky is more open, and I'll talk a little bit more about this later, but then the RTK GPS will be the easiest and fastest if you have a clear view of the satellites, and preferably if you have cellular connection. And then the only time you're going to use the total station is if you have pretty good visibility over a good distance, so that I would not use a total station if you think you need more than 3 setups. Forget it. 1 setup ideal, 2 okay, 3 because you really believe in it. No more, because it takes too long to move a total station and reoccupy it. Beyond that, just do the auto level, get the data, and move on. We need to get to too many sites to get too pedantic about the data at any one site. Next, you recon the site to evaluate if the channel is entrenched into the valley floor. And of course, if it's entrenched, can you walk along the valley floor out of the river corridor? Is it all blocked by fences or buildings, or what's going on out there? You need to recon the site to determine if it is a split channel. You have to evaluate if there are bed undulations like riffle pool or width undulations. And then you have to work through the decision tree to determine what I call the characteristic width. Finally, you compute the site length as 15 times the characteristic width. If it's bigger than 200 meters, you just stop at 200 meters and you measure the whole site. Okay, so the nearest urgent care facility, if somebody gets hurt, generally from the 9-county Bay Area, we're in a relatively urban area, it's most likely that you're going to be able to drive to a location. I have a separate field safety plan for the project. Everybody on the project, if you're going in the field, you're required to read, understand, and be able to implement on any given day you're out there that safety plan. Everybody needs to understand and read the plan. And so the one of the components of the plan is just if I'm at some field site, like over here on the right, okay, look, it's only 12 minutes, 5 miles to get me to this hospital over here and to the urgent care. So, like you just have to figure out where that is. You just have to know the name of it and write that down, because if you know the name, you can always type that into Google Maps and go. Now let's talk about qualitatively assessing if the channel is entrenched. In the image on the upper right, we have a small channel and it's adjacent to a grassed over point bar, and then what looks like a little bit of a slope on the right, but probably could be floodplain. It doesn't really matter, but we have a really low height, like from the thalweg to being out onto the grass is a very small height. So if we measure the width of the channel and you go up double the depth of the channel out onto the floodplain, it immediately gets very wide. So this would be a low entrenchment scenario. In the bottom, you look here and you can see that the valley floor is maybe 3 times my height. So, I'm less than 6 feet tall. So it's at least 20 feet, could be even 30 or 40 feet to get out of here. So probably quite a bit. So in this case, we would have a high entrenchment, like the width of the bed and then the width even halfway up this thing, it's not much different. So this is a highly entrenched on the bottom. This is very low entrenched. And then you could just imagine some intermediate scenarios. And this is a diagram from Rosgan's textbook, just illustrating some different examples of entrenchment. I want to clarify that entrenchment is not the same as confinement. So in this photo on the left, this to me is actually confinement, where you have like a hill slope and a valley, and if the river fills the whole valley floor like this, and that could be really small, like a small V-shaped, you're way up on a hillside or something. To me, this is more a measurement of confinement. So in any case, entrenchment to me is more about an alluvial channel within an alluvial valley. How much is that entrenched? It's not like, okay, if I have a bedrock river in a canyon, is that I don't worry about that. Well, we can measure confinement of a channel within a valley on desktop GIS. So we're not here to assess that. We want to know if the channel within the valley floor is entrenched down through the valley floor, like you see in this bottom right photo. Next, you want to assess if the lateral zones are walkable. Lateral zones being stream bed, the river bank, the valley floor, terraces. Like in this photo in the upper left, it's all easily walkable. No problem. Sky is wide open. This is RTK all the way. In the bottom left, it's walkable, but there's an awful lot of tree cover. The RTK may not work, but the total station would work great here. Maybe you get a couple of benchmarks and coordinates from the RTK, you set up the total station and off you go. It's all walkable. What's not walkable is a place like this. In this case, I'm just completely surrounded on all sides by vegetation, tree trunks, roots, and you can just see like you can barely get into this channel. In a case like this, the RTK isn't going to work. The total station is a complete waste of time. So you would want to do the auto level, or we may just decide, look, this is ridiculous. I mean, why even bother with a site like this if we don't have to? If we have many examples, alternative places of this stream type that are walkable, then we would prefer to do that. On the other hand, maybe this stream type, maybe that's the whole point of the type, is it's entirely overgrown, and that's the nature of this type. Then we'll have to fight through it and use the auto level and get the data. Okay, so all methods require a site to be walkable with reasonable views along and across the stream, not too much poison oak or blackberry. So we want to determine what is the suitable surveying method. There's just no way around it. I mean, if it's not safe, if you're on a cliff edge and whatever, or it's like, I don't know, whatever the danger is based on your assessment, if you decide it's not safe, it's not safe. If you decide it's not walkable, then it's not walkable. Then we have to find another site. So assuming it's walkable, you're not going to die or whatever, get hurt. The next question you ask is, do I have a clear view of the sky? Yes, I have a clear view of the sky. Okay, if there's a strong, reliable cellular service, then use the RTK GPS tied to your cell phone. We may have a mobile hotspot. I don't know, probably not, but like most of us have what's called tethering in our data plans. The RTK is like just SIPs data. I mean, it's not like downloading a movie in 8K or something. I mean, it's like pretty sippy. You could always like use it for a day, go to your wireless plan and see how much you used the day before to see if it was a problem or not. In any case, yeah, clear sky, you're in the Bay Area, it's got cellular connection, use the RTK. If there's no cellular service, it's still possible to use the RTK if you have a clear view of sky. What we have to do is we have to take one of our units and set it up as a local base station. We have to then set up radio communication between the two units. And then we can use the other one to collect data. Currently, I haven't set it up. I mean, it's like April 16th. I used to do all my surveying this way, but I don't have it set up. I don't know the status of the radios, so I'm not sure if we'll be able to do that method or not. But if we can, we'll add it to our wheelhouse. Now, let's say you have a limited view of the sky. If there's clear line of sight down the river and across the river, it's not like, oh, I can see, but no, if there's vegetation everywhere, like you need to be able to see such that you can see at least a third of the river. And with just 1 to 3 views, you can see the whole of the site for all the transects you need to do, then use the total station. If it takes more than 3 viewing locations to see the river, we're not going to waste that time. We have too many places to go. Like more data is more important than 3D georeference data. So if there's more than 3 viewing points, we're going to use the auto level because it's just the fastest, simplest way to get the variables we need for our project goal. Okay, next you're going to assess if it's a split channel. So what is a split channel? Well, of course, so you just have a river and then there's islands. And of course, because of like the dry climate we're in, the whole riverbed might be dry. Just a small deposit in the middle doesn't matter. But I'm going to differentiate where if you can identify either an active width or a bankful width, if the island or multiple islands, if they don't cross over high enough to really make it 2 totally different channels, then you just follow the normal protocol and we pretty much just ignore this. Like you just get your You just get the left riverbed on the left, you ignore this island, you get the right riverbed on the right, and then otherwise every higher level you just get it. In this type 2 channel, if the island, like, it crosses over so that they're two fully separate, now we're going to denote a left subchannel and a right subchannel, and you're going to survey both of those with like a split channel protocol. So, like, left split channel, this is the left split channel, this is the right split channel. Then you'll have to have the left bank of the left split channel, the right bank of the left split channel, the left bank of the right split channel, and the right bank of the right split channel. So it gets more confusing. If you had many, many islands, like if this was, a multi-threaded river. I don't know if we have a case like that in the Bay Area. I don't think we do. I think on a case-by-case basis, we would decide how far we would take it, like left, middle, right, or something. But basically, just talk to me and we'll decide how we want to handle it. But in general, for a small island that doesn't protrude up all the way to a bankful or active height, then just do the normal protocol and ignore the island. It's not essential for, again, the main purpose of our survey. Okay, next, evaluate if there are bed undulations. It's sort of a yes or no question. Undulation refers to if the bed elevation changes along the river. So if we look from the side, what we call the longitudinal profile, we're looking for like a pull trough or a riffle crest. And again, like I want to be very clear, we're talking about the overall structure of the entire landform of the river. I'm not talking about that there's one boulder and that boulder is a crest. A crest pretty much blocks almost the full width of a river. If you look at this photo in the upper right, you see this huge deposit of coarse material making the riffle. Yeah, there's a thread, shoot, we could say, on the far left and on the far right where it's kind of going around it, but even there, the bed is higher. And then downstream of that is the pool. You can contrast that with a relatively uniform river. So in this bottom photo, the bed is rough. Like there's a lot of boulders in the channel here, but there's no bed undulation. So the undulation is not asking you, are there large bed elements like boulders and wood? It's asking, is the entire landform itself undulating as a bed undulation? And typically you'll see that the riffles are coarser sediment and the pools will be finer sediment. So first it's just yes, no, are those present? Similarly, are there width undulations? So for example, in this photo, let's just assume it goes from right to left. It's relatively narrow between this forest, like the hillsides are coming down and it's narrow, and you come down a little ways and then it's quite wide. So we have very sizable undulations. Now, the wider the river, with a really wide river, proportionally, this undulation from here to here, it's like a factor of 2. That's pretty significant. In this bottom photo, we have a narrow river, but it's pretty much just a ditch. So there are always going to be some wider spots somewhere. But the main point is for this channel, it has low width variability. Okay, so I want to clarify again that I'm about to go through the protocol of deciding what is the width or characteristic width, but I want to be very clear that 200 meters is the maximum site length we're going to survey in the field. Why? First of all, our intervals, our stream intervals for prediction are 200 meters. So going longer than that could potentially start to violate some of the assumptions. Being shorter than that is okay if the place looks pretty representative. I don't know. I mean, if there were like 3 or 4 dramatic changes within a 200-meter section, I guess I would start to be concerned. That's why you're going to have photo documentation of the sites. But, you do site recon. When you get to a site, you say, okay, well, what is the most representative portion of this? And then once I find that, what's the easiest way to hit this whole area? And then that's what you pick. But at the bigger end, we don't have the capacity, the time, the resources to if it was a 300-meter wide river to then survey for 3 times 15, one point or 4.5 kilometers or whatever it is. So that's not the point of the river. I mean, of the study. Um, if we do get to some of our largest rivers and we need to do boat-based methods, we'll implement a boat-based protocol at that time. So stream intervals for machine learning prediction, they're 200-meter longs. Therefore, sites will only be observed up to a site length of 200 meters. We're not going to go bigger than that. It's the same limit we used in the statewide survey. And if we need to go bigger than that, like if you come to me with some explanation, we can look at it thoroughly and make a decision on a case-by-case basis. Okay, now we have the decision tree about the width problem. The width problem is that we have so many different kinds of rivers, there is no one yardstick, okay? Bankfull channel does not exist in a concrete rectangular channel. It doesn't make any sense. And since we're measuring all these different kinds of channels, then we can't have the same yardstick or create a myth, right? We have to go with reality. So I have a decision tree to get to what I'm going to call the characteristic width that will be used to determine the site length. That's all we're doing right now is just we want to know how long the site is. So go to a place at the site, it almost doesn't matter where, and ask yourself the first question: is the channel composed of an artificial bed or banks or both? If the answer is yes, then if it's a rectangular or trapezoidal channel, that's the next thing. Ask yourself, is it rectangular? Well, it's not, is it this or that? Is it rectangular or trapezoidal as opposed to anything else? If it's rectangular, if it's trapezoidal, follow this protocol. As shown in this diagram, you want to measure the width of the bed. We're not going to use the bank top width in this case. We're going to use the riverbed width. So you could measure that with the laser rangefinder, or you could measure it with a tape measure. We're just trying to get a characteristic width. I mean, the fact is, if it's rectangular or trapezoidal and it's concrete, guess what? Every cross section is going to be almost exactly the same. So we don't have to get all concerned and pedantic. We just get the riverbed width. We go multiply that by 15. Well, okay, so you do that 3 locations, each location at least 1 riverbed width apart. So what do I mean by that? If the riverbed width is 10 meters, take that cross section and turn it till it's going up and down the river and walk, by eye. We don't have to measure it, but by eye, if the cross section is 10 meters wide, walk 10 meters down the river and measure the width again, or 20 meters, whatever you want. It's just at least enough to try to get away from your starting location, and measure it 3 times. If you're in a concrete ditch, it's going to be basically the same, but we're just trying to be careful. If you're in a natural river, as we'll see later in the protocol, yeah, measuring it 3 times is pretty useful. Take the average of those 3 measurements as your characteristic riverbed width, multiply it by 15. Again, if this number is bigger than 200, it's 200. If it's less than that, it's whatever the number comes out to be. Now, what's the alternative? Well, if you have an artificial bed or banks and it's a triangular channel, there's no riverbed width. So we can't use it. Now we have to use the bank top width. But with a triangular channel, the reason why we're not using the bank top width here to standardize it is because this is going to be pretty wide. You're never going to have a bank top width of a triangular channel, because the triangular channels they're almost always equilateral, or what, like you see here, right? So these 2 sides are going to be the same length. You're not going to see an asymmetric. I've never seen an asymmetric triangular channel. So to be triangular like this, yeah, we'll use the top width for that. Again, do it 3 times at 3 different locations, at least 1 width apart. Multiply by 15. If it's less than 200 meters, that's your site length. Now, if step 1 is It's not artificial. It's the bed and the banks are natural. Now you move on to the next question. Is the channel entrenched? If the answer is yes, we have to have another question. Does the channel have an inset deposit? Well, what's an inset deposit? Okay. Well, first of all, what's not an inset deposit? So in this photo that I showed you before, it's just incised down and there's a bed. You have a bed, everything else is erosive. If there's no inset deposit, you just use the bed width. In fact, in this case, it's almost no different. The fact that the banks are artificial versus natural, you're going to use the bed width, and we're going to multiply that by 15 and get our length. If there's an inset deposit, what I mean is like that, it incised, but it's also had periods of aggradation, alternating aggregation and deposition, or maybe it incised and the banks have been collapsing, and now you have an abundance of sediment that makes an inset deposit. Some cases, this could be what's called a bench. Some cases, this will be a point bar. It could be an island. But when you have an inset deposit, now you have a chance where maybe you're thinking about, okay, what's my active width, or do I have a bankful width here? So does this channel have an inset deposit? That's the no side. But now what if we answer yes? Yes, there's an inset deposit. Well, now I have to worry, wait a minute, is my deposit making a split channel? If it's not making a split channel, go on to step 5. If it is, we'll go on to step 6. See, it's getting complicated. And all we're doing is we're just trying to come up with a width. Okay, so there's an inset deposit and there's no split channel. Then what do? Now you look to see if there are bankful indicators in that inset deposit, revealing left and right locations and with about equivalent heights of the bank stage. So if anywhere along your site, you don't have to find bankful everywhere, but if you go along the site and you see it in a couple places, then you can measure that bankful width and average the locations where you can measure it, multiply times 15. If there's no bankful indicators, then look at the active riverbed sediment, measure the width of that riverbed sediment, and take that active width, multiply, measure it 3 times, take the average, multiply by 15. And so, yeah, okay, so we haven't even gotten yet to the split channel part, step 6, but I just want to now talk a little bit more about bankful. Like, what are you looking for? So I have some more images to help you see bankful. In this case, we've got an asymmetric river quarter where we have a hillside on the right that's been erosional. And then on the left, there is a flat depositional surface, in other words, a floodplain. And we see a bank where we have active riverbed sediments, the gravels and cobbles. And then you have a very sharp line of the flat surface to the slope bank with that riverbed sediment. So we have a clear bankful indicator on one bank, but not on the other. But that's okay. So you would do your best, like you could use the rangefinder, you could use a tape measure and measure that width. And then here's another location farther down where there's a point bar, and it's kind of hard to tell, but it is a sloped bank as well. And then there's a transition line there. And again, measure the width at that location. Here's another example. This is incising potentially a little bit, but we have an outer cut bank. We have a point bar, but the point bar is set a little bit high. But in any case, you've got the flat top of that point bar. We'll call that bankful. You go across and you get your width. And here's another example. All this is like the lower part of a lateral bar or point bar, but it's also could just be the riverbed. I would call it riverbed anyway. And then, but it is sloped. So anyway, it could be somewhat depositional. But we're not up onto the floodplain until you get to the end here. and we have our bankful stage. Okay, so now I think this is it. This is the last step, I promise. It's the split channel. If you have a split channel, if it's type 1, then you ignore the island in the middle. You measure your characteristic width as either the active width or the bankful width. If it's split in two, though, this is where you have to now measure both. You have to measure the left split channel and the right split channel, add those two widths together, ignoring the island. Like, don't count the width of the island. You would add those two widths together, and that would be your width. So I think I say some here. Measure it for both, sum the parts together, repeat it 3 locations. I hope that's the last step or you're going to kill me. It is. Yay. Okay. Ooh, that's a lot of steps. I guess I should just quickly review. I mean, it's just to determine how long the site is. If it's artificial bed and banks, it's probably rectangular, trapezoidal. We'll have lots of those. Just get the riverbed width, multiply it by 15. If it's triangular, bank top width, sorry, multiply it by 15. If it's an entrenched channel with no sediment, get the bed width, multiply by 15. If it's incised, but it has an inset channel, look to see if there's bankful indicators. If there are, take the average bankful from 3 locations and multiply by 15. If there's no bankful indicators that you're satisfied with or confident in, get the active bed width 3 times and multiply by 15. And if you're in a split channel, only measure one width if the island does not get as high as your width, line. If it is a type 2 split channel, measure both portions, add them up, multiply by 15. All right, exciting. Allergy season. Okay, so what does this look like as a data sheet? So I've just finally finished the general site assessment part of the data sheet. So we have the date, site ID, stream name, crew member initials, GP, KR, NK, ZW, whatever. Your nearest urgent care facility by name. Now, these are the qualitative variables, and these are very, very useful. We can use these for our classification. Entrenchment, high, medium, or low. Artificial bed, oops, that should have a YN. So yes or no, artificial bed, yes or no, artificial banks. Is the valley floor walkable, the river bank walkable, the stream bed itself walkable? Split channel, no. Type 1, type 2. Bed undulating, yes or no. Width undulating, yes or no. Inset deposit, yes or no. Bankful indicators, yes or no. Now you have to go through the decision tree to pick your characteristic width and measure it 3 times. I tried to make these spaces wide enough that you could write all 3 numbers and take the average on the sheet. You only need one of these 4. It's like either it's artificial bed width, it's a natural entrenched channel with no inset sediment width, it's a bankful width, or it's an active width. So it's one of those. Then you take whatever the average number is, you multiply it by 15 to get the site length. If it's bigger than 200, cut it off, it's just 200. You take that 200 and divide it by 9 to get our transect spacing. The next question is asking something for later on we haven't covered, which is if the widest location is at one of your equally spaced transects, then just write the transect number where that is. If the narrowest is at a T transect, write where that T transect 1, 2, 1, 2, whatever. I'll explain this more in a little while. I also, as far as just a reminder, I want you to take a photo looking upstream and looking downstream from every transect. Could be in the middle of the river. Maybe you alternate, like middle of the river, from the bank, whatever. But we want lots of photos. Like photos are very, very important. And then on the way out, take overview photos. Like try to get up somewhere higher and get some good just overview photos. So these last 2 parts of the general site assessment are just to like remind yourself to take those photos. Okay, we're up to the next part of it, which is locating transects. Where do we put our transects? Really simple. Equally spaced transects. So first of all, you calculate the transect spacing as the length of the site divided by 9. There's 9 gaps to get 10 transects. If the bed is undulating, T1 needs to go on a riffle crest. So if you have a repeating bed forms, like go find the full landform riffle crest. And I want to point out, you can also have steps. Like if you have a step pool or step plain bed or anything like it, T1 can go at the crest of a step. So you locate T1 first and put a flag down or tie off some flagging so that you know where T1 is. Now, we set flag 1 on one of the banks of T1. Take your photos from T1 looking upstream and downstream. We do have cameras, or you can use your cell phone, whichever way you prefer. Now, from T1, use a tape measure to locate T2 because you have to follow the curve of the river. Now, one of the complications here is, do you follow along the thalweg, the left bank, or the right bank? You look at the banks, for example, on the inside of the meander bend, the bank is shorter, and on the outside of the meander bend, it's longer. All that matters is that we take a consistent approach. You know, you may be at one site where the left bank is just a steep cliff covered in blackberry thorns, and there's nothing you can do. We have to be somewhat pragmatic, like what will work at a site. I wish we could perfectly standardize everything the same everywhere, but it isn't realistic. So pick a side and measure the distance all along that side, at least consistently there as best as you can. So after you use your tape measure to get the length divided by 9, go to the next cross section, set your next flag, and then you just, you just repeat this procedure, take your photos, set your flags, and work your way down the river till you have your 10 transects so you're laid out. My personal preference, although it's time consuming, will be to pre-lay out the site interpretation rather than doing it as you go along. But I think as you get more experience, you'll make this evaluation yourself. I've added a note here, a decision we've taken that if the stream is entirely concrete, we don't need 10 transects. I mean, it's concrete. It's all the same everywhere. Okay, if it's undulating, fine. But I mean, if it is a uniform concrete channel, we're only going to do 5. As a result, you would do L divided by 4, I guess, and you would just have 5 transects spaced out. I still want 5 because mathematically, we still want to take an average and, have confidence that we've measured that well. Now, we also are doing a procedure in which we're adding more transects on what we call a feature basis. So a feature being a pool, a riffle. So we have 4 kinds of features: pools and riffles. Riffle could also be replaced with a step, like the crest of a bed step. We're then going to have the widest cross section and the narrowest cross section. So I don't want to represent every width undulation. We do want to represent every bed undulation. So we've done a lot of studies that show especially that there's greater sensitivity in our stream function analysis to bed undulations. I mean, if we have a site that has a lot of undulations, eventually, if we're going to model it, we'll have to go back and get all the width undulations too. But in the first place, I do want to get the maximum width of the site as a metric. So if we put a maximum and minimum, I should say also, put a flag at your widest cross section, your narrowest cross section. If the widest cross section is at a T transect, that's where way, way long ago, I had something on the protocol here. If the widest transect is at a T transect, just write the transect number like T5. And similarly, if the narrowest is already at a T transect, do that. Similarly, if a pool, if the trough of a pool happens to be really, really close to T6, fine, then use T6. But like in the example here, T6 is at the edge of the pool, but like it gets a lot deeper downstream. Then you need to add a pool transect. Same thing for a riffle crest. If they're like within a meter of each other, like, no, don't bother with it. But, beyond that, I would, add an extra flag and transect for where those are. You'll have as many pool transects as there are landform pools, not scour pools, not because there's a little cluster of logs or something, but a true channel landform pool and a riffle. It's easy for me to sit here in a presentation in an office and say this, but you will have to work together as a crew with your leaders, like making your scientific decisions and interpretations for what to do. Okay, so you set the flags in all these riffle crests and pool troughs, set a flag at the widest and narrowest location. We'll name the pools from upstream to downstream, P1, P2, P3, and so on. Riffle crests, R1, R2, R3. We just go in downstream order, and that's pretty much it. That's the layout of the whole thing. If we look this in longitudinal, maybe you'll get something like this. Each of these black triangles is showing you the location of where your equally spaced transects are. They're just going to hit wherever they hit. Then we'll have the pool troughs like in red, the riffle crests are in purple, and the wide and narrow, just as an example, are at these two locations. All right, so now we're up to what do you do at those transects? You survey them. So what does that entail? I'm going to focus on the river science of it more than the methods. I'm not going to teach you how to use an RTK or a total station in this presentation, although I will do a little bit with the auto level. Let's start by making some definitions and differentiating what we really, really, really want and then what we'd like to have if present. At all 10 cross sections, plus any undulation, pool bottom, riffle crest, wide, narrow, and like every cross section, the goal is to have at least 5 points. The 5 points being the thalweg being the lowest location, a left and right riverbed toe, and then a left and right valley floor slope break, which might be a riverbank. It might be the terrace. Like, I don't know what it is, but it's your outermost, like whatever the outermost thing of the river quarter is, unless it's like 5 miles away or something, but yeah, we're in the Bay Area, so we don't have to worry about that. So at least a 5-point survey, and I'll give you some specific examples, but the key is I define a toe as the slope break where you go from a flat bottom to a rise, and then a top is where you go from a rising lateral slope to a flat outer surface, I guess you could say. So we have toes and tops. So a thalweg, a left and right riverbed toe, and then a left and right valley floor slope break. Like that is the 5 minimum points that we should have at every transect. The only time you might not have it is if the valley floor edge is too dangerous. Like you just can't get it. It's too high or whatever. But still, like I do have an alternative in that case. So I'll get to that. You're pretty much always going to have at least 5 points. Now, if present, if there's an inset base flow channel, and I'll remind you of what that is shortly, give me a left and right base flow channel toe, BSTO, and give me left and right base flow channel tops. If you see an active channel indicator or bankful channel indicator, and they're higher than the riverbed, like if all you have is riverbed is the same as active, it's the same thing. Then if you just have a riverbed toe, but hopefully we see a surface higher than that, and you decide it's either an active top or a bankful top, then you've got a left and right of those. If there can only be one, though, it's like either active or bankful, and there's only one. There's not bankful 1, bankful 2, but no, there's just bankful. However, with terraces, you could have more than one. Maybe you have 2 terraces, 3 terraces. In that case, it'll be like TR1, TR2, TR3, and every terrace will have a terrace toe and a terrace top, and left and right. Okay, let me show you examples. And we're gonna need to add more to this. Like, this is just what I've thought of so far from our visits. But most important, okay, here is the rule you should say every time you go out. Please get what you can, but safety first. I mean, if this project isn't fun and educational, then it's not worth it, right? It's not worth it at all. Like, our lives are much longer than this project. So if we have 10 cross sections, 15 cross sections, and you're like, hey, there's 4 cross sections here, I can't get the valley floor. Okay, then don't get it. Don't get it. We have a variety of methods. We'll try. But, if you can't get something, you can't get it. It's okay. Okay, so realistically, some transects will have points located in conditions that are too difficult or unsafe to measure. For example, it's too high. I don't have the 50-foot ladder. We're not rock climbers. And what if the whole cliff falls apart? It's too steep. There's private land we couldn't get permission to go on. There's barbed wire fences or electrical fences. There's massive amounts of poison oak. Or it's just, there's, like thorns or whatever. Whatever it is, if it's just can't be done, it can't be done. Get what you can, where you can, with a priority on the 5 essential points: Thalweg, left and right riverbank, and something higher, a valley floor edge. Get what you can, where you can. If you can't get those, you can't get them. I mean, if the river's 30 feet deep, how are you going to get the Thalweg? Just make a note, and I'll either come back with a boat and get it on my own, or something else. Why am I saying that? Because we're going to produce site average variables anyway. And so if we have, 4 or 5, it'll work. I would prefer to have 10. I'd prefer to have them all, but get what you get. And we'll, on a site-by-site basis, we'll decide how to handle it later. Now, of course, if you go somewhere and you're getting like 2, and it's just not working, then the site isn't viable. I mean, we can't burn it all down so we can survey it, right? So get what you can get. If the site is not doable, we're going to have to throw that site in the trash and find a more viable site. Okay, let me show you some examples. So the simple case, here's an unconfined channel with a wide open valley floor floodplain. It's just a 5-point survey. Give me a Thalweg, give me a left and right toe, and give me a valley edge on the left and the right, which I would call bank top. It doesn't really matter if you call it bankful, valley floor edge, or whatever. It's just the top that's here. We're not going to walk a kilometer out and go get the far valley floor edge. In fact, we already have that. Okay. We've already extracted the width of the whole valleys from the 10-meter DEM. So we don't need that. We can't see entrenchment in the DEM. So anything that's like trenched in the river corridor, that's what we have to focus on. But in this case, just give me your 5-point survey. If you want to call it a left and right, bankful, that's fine. But otherwise, if you're not sure about bankful, then just call it the valley floor edge, and that's it. That's all we need. Why with this alone, what can we get out of that, Greg? Like, what do we do? Well, from this alone, we can get a riverbed width and depth. I mean, if it's totally flat, then the riverbed depth is 0. But if the Thalweg is a little lower, we'll get some kind of depth measurement for the riverbed, and we'll have a width of the riverbed. We can get a river corridor width and depth from this. And not only that, it's like we can get the average across all transects, but we can get a standard deviation. We can get a coefficient of variation, a max, a min, a skewness. Like, we can get all kinds of things. We can also get the entrenchment ratio. We can also get the longitudinal channel slope and valley slope, if those are different. And depending on the survey method, we also may be able to get channel and valley sinuosities. So that's a lot of data from 5 points, like times 10 transects or something. What about an incised river? Okay, well, here's like an incised river in the photo on the left. Same thing, just give me my 5 points. Thalweg, left riverbed toe, right riverbed toe, and then left and right valley floor edge. That's all I need. Give me my 5 points, and we're all set. Here's another scenario we've already observed in the field. What if the bed is sloped? If the bed is sloped, that is fine. The left and right riverbed toe have the unique relationship, I guess I would say for the valley floor edge too. The valley floor edge and the riverbed toe are unique in that they don't have to be at the same stage. They don't have to be horizontal. In this case, I made it so that the left riverbed toe is the same as a thalweg. That's fine, but record that location twice. So if you're using an RTK GPS, give it a code value of TH first, take your point, the point number increments, now change the code to L RBTO, take another point. So it's collected twice. Hopefully it isn't shifted too much, but yeah, in any case, or same thing with the auto level, just take the reading twice. That's the only time the bottom and the top do not have to, they don't have to be aligned, but everything else has to have a pair on the left and right side. So the riverbed toe can be sloped. All the other things are going to have the pairs. I'll show you why. Okay, thalweg. Yeah, that's the same point. Measure twice. Okay. The next is an example of an inset base flow channel. This can happen not only in artificial channels, but in natural channels, but it's very common in artificial channels. So in this case, you have a thalweg, which would be the bisector because it's just flat. We've got the left base flow, like BS channel toe, the right base flow channel toe, the left base flow channel top, the right base flow channel top. We've got the left riverbed toe and the right riverbed toe. And then you come all the way up out of there and you give me your left and right valley floor edges. So it's the 5-point survey supplemented with the 4 points required to see the base flow channel. This is a little bit more sophisticated, but this is a picture I showed you earlier, and now I've layered on my points. So let's work on it. So from the bottom, the thalweg, my left and right geometric base flow channel. Not where's the water, but where do you walk around there? Okay, I see my slope breaks. Give me my left and right base flow channel toes. Give me my left and right base flow channel tops. Give me my riverbed toes, left and right. And then at the top, now we call this bankful. So it's my right bankful top, my left bankful top. And then I'm just going to call this right valley floor edge, left valley floor edge. They don't have to be at the same elevation. They're just telling me that these are the width of the slope break. I can't see what's going on past on the left. Again, we're not going to walk a mile to go find the valley wall. We've got the valley walls already. We don't need those. Okay, now here's the complicated scenario. The complicated scenario is when one bank is steep and the other bank is not. So if we have an inset deposit, this is the most likely scenario. It's like you've got an incised river with an inset deposit. So let's work from the bottom. We've got our thalweg as our deepest place. Let's say you see the sediment and we've got the sediment indicating our riverbed toe. Then we see a slope break. Now on the left, I'm assuming for the moment, our left and right toes do not have to align, but I'm just showing here that they did. The next problem is your bankful. So you hit the bankful top and you have a very clear indicator here, but what do you do about the other side? We must have a measurement on the wall. Again, if it's not safe, don't do it. Only do the one side. But with only one, I can't measure a width. So, it's not so useful. With this case, I'm assuming not that you're going to climb up this wall to get to that top, but I'm assuming that there's some other safe way to get to the top of the valley floor. Again, the valley floors, they don't have to be aligned, although that I've shown them here. What I'm really emphasizing right now is what do you do when you have this one point? And so the method is, to the extent possible, survey location on a transect should be left and right pairs, except the Thalweg. So how do we do this? Well, what we're going to do is use a builder's string line, which I'll show on the next slide. But basically, you're going to hammer something over here, a stake, and then you're going to run a builder's line across, and somebody's going to look perpendicular at a level bubble. And when it's level, we'll just make a mark there, or somebody will come over with the surveying instrument, like, I don't know, the RTK, a prism pole, or auto level pole. We'll stick it there and we'll make the measurement. Okay, so here is that demonstration. So you put the stake in, you run the line across, and you've got your level bubble on there, and you just get it aligned, and then somebody has to hold something over here that you can survey it. Once you survey that, we have everything we need. That, I feel like that's really one of the hardest things of the whole protocol, but I don't see an alternative, or else you don't have, like, just only having one of these isn't useful. I mean, I don't know. You'd have to like take a top and a bottom and make an interpolation and all this extra work, but you have to be respectful. Like, it's always easiest to do something in the field than it is to do it in the office. We'll fix it in post in the office. Like, no, we're not going to know. We're not going to remember. It's not documented well enough. It's really hard to fix things later. It's best to put the work in up front and get it right in the field. I want to show you a couple of difficult cases. And one of those really difficult cases is a natural V-shaped channel. I don't know that we're going to be going that high up into hillsides and having like this, but I'm just trying to be prepared. Of course, if it's a completely cement channel, you can get a Thalweg, but if we're a completely cement channel, you got nothing. I mean, there's nothing to tell you. There's no active width, there's no riverbed width, there's no bankful width. Maybe there's a top, and I guess if it's triangular, if you had a Thalweg and a top, a left and right valley floor edge. I should have added those. I don't know why I didn't, but if you have a left and right top, then if it's a concrete channel, that's fine. But in a natural channel, this could just be sheer, these could be hill slope walls going up, really far. So what I'm hoping is, in a case like this, you'll be able to see some indicators of an active channel. Usually you can, even in a V shape. And so you measure your left and right active. Again, those have to line up. And then you measure how high that is above the Thalweg. If you have a data collector, you just look at the values, and then you double that height. You double that height and take another measurement up there. So I'm calling this 2 times active with like 2 times AC top, left and right. At least this gives us a way to measure an entrenchment ratio. It's helping to show the V shape. Again, it gets us to a 5-point survey. So it's hard. Measure the Thalweg, try to find indicators of an active width, take notes of these elevations between the active elevation and the Thalweg. You could take the average of the two sides if you want, but hopefully you just put the auto level or the level line level or something to get those the same. Then you compute the height, you double the height, find that height, and then measure the left and right sides. Another difficult case that I've observed is, like, if you have a very wide riverbed, compared to the valley. So if basically the channel fills the valley, we have this problem again where you've got a clear indication of an active width based on the bed material, but it's basically just the bed, it's the riverbed. So the left and right riverbed toes, like you see all this active sediment, and then you go from that active sediment right to a hillside that's just grass and soil or something like that, or maybe it's just bedrock. There's no active channel. The active channel is the riverbed channel. That's why I've put them with the same code. So in that case, again, measure a height, double that height, and give me a shot on either side at that height, sort of the procedure. So there's no banks. You just have, you're filling the valley floor as such as it is. Riverbed equals active width. So measure Thalweg. Give me the points on the left and right. You can duplicate survey them as riverbed and active if you want. I think I would prefer that. And then double the height, find those locations on the wall and survey those. Okay, this is like the grand finale. Everything, everywhere, right? Okay, so we start with our 5-point. What do we got? 5-point survey. Thalweg, riverbed left and right toes. We have an active channel, tops. So that's already 5 points. I've stretched my builder's tape to get this steep bank. Now I've got a floodplain. And then the outer edge of the floodplain, we don't call that a floodplain edge. We call that the terrace toe. Oops, it's missing. There should say TO. This is terrace 1 toe, TO. Oh, that's right. The O, it got squished and put the O here. Sorry. So this is the left terrace 1 toe. And because the floodplain is sloped, it's not exactly the same there. It's somewhere up here. Ideally, if this isn't too wide, you could stretch the builder's string. I mean, I think I've got a 500-foot long string, although I don't think we'd need it that far. Find the other side and give a shot there so you can get the width of the terrace toe. Go up to the top. You have the left and right terrace 1 top. Go to the outer edge. You've got the terrace 2 toe on both sides, and then the terrace 2. Well, and then, oops. I don't have a terrace 2. There should be a terrace 2 top here, but then you'd have to find the pair on the other side. And then I've just on the, I think, yeah, and then I've got in this case, I have an outer valley floor edge, but again, we don't even need that. So I was just giving you a maximal scenario. Hopefully we don't have something like that, but we might. In any case, you just keep going up the terraces, getting toes and tops. Okay, so what does the data sheet look like? So first of all, the RTK and the total station don't need data sheets because the data is stored on the data collector computer for each of those. However, in the setup of those instruments, you have to record the height of the rover pole and the height of the base unit pole. And I've just given you, 1, 2, 3, 4 pairs of those in case you change the pole height for any reason. So you can write that on the piece of paper in meters, like 1.245 meters. And remember, for the RTK, you have to press M, so 1.245 M. For the total station, you need the height of the instrument, the height of the back sight rod, the foresight rod, the back sight rod, and then I've given it for 2 setups. If you need a 3rd setup, fine. More than 2, 3, forget it. And then if you, throughout the day, you'll make various backside checks, write down the horizontal and vertical offsets of those backside checks. Okay, the auto level. Auto level is the easiest instrument. It's the fastest. It's reasonably informative, but not entirely informative. The time when we would use the auto level is when we can't see the sky and we have poor line of sight. So you have a meandering river. I mean, this is only 5 cross sections. If you need to do 3 setups and 5 cross sections, meaning 6 setups for 10 cross sections, we're not doing a total station. We don't have the time to do those setups. The auto level, you just throw it down wherever you feel like within some view. So for example, in this case, in orange, transects 1 and 2 are visible from here, but I can't see all of the other transects. They're blocked by vegetation or the walls or whatever. So I set up at site 1. Now I need a match point, and I'll explain what that is shortly. So it doesn't really, set up whatever height, whatever, you set it up, you just get it level. The first thing you do is find a location between your first and your next setup and make a match point location, make a mark or something. And then from setup 1, measure the height of the rod at match point 1. Now go ahead and survey. Do not survey and then get your match point, because what if somebody kicks the auto level and you lose all your data? As long as you set up match point 1, you can get a new match, you can resurvey it at a new height and it still be match point 1 and keep going. So set up 1, match point 1, do your data collection for T1, T2. Now you're ready to move on, move it to setup 2, backslide over to match point 1, take the elevation at the new location, survey the purple transects T3 and T. Well, no, I tricked myself. Get your match point 1. Now turn and go get match point 2. Get your match point before you do your data. Now survey transects 3 and 4. Move to setup 3. Shoot back to match point 2. If you're continuing on, shoot on to match point 3. And now get the transects you can see from setup 3. If we look at this longitudinally, what am I talking about? The riverbed is sloped. So as you do your setups, let's say you're going down the river, you have a match point. If I have an auto level, and I have a rod, I can read it. And let's say that the rod is 6.5 meters high, or pretty high. Let's just say it is. And that's where we are at setup 1. Now at setup 2, I go set up there and I measure it's 4.5. Well, what I know is that all data I observe from setup 2, I have to raise that data up by 6.5 minus 4.5 equals 2. I raise all those number height. Wait, well, all the heights, everything has to go up to match. Yeah, so the numbers everything has to shift to get to that. Now you turn around, you have 9.6, you have 3.7. You figure out, we don't want to just align with the purple data. We need to align with the orange data. So in this section, we have to do 6.5 minus 4.5, and then add to that 9.6 minus 3.7. And we get a net effect of shifting all the data up by 7.9, if I've done the math correctly. Anyway, so this is why we have the match point, so that we can shift all the data up into one same horizontal datum. Whether it's add or subtract or whatever, it all makes sense when you look at the numbers, but that's the basic idea. Is like the match point, if it's 6.5, from 4.5, you have to add 2 to get it to say 6.5. And yeah, that's what we have. So what is the auto level has its own data sheet because it doesn't store anything on it. On its data sheet, the columns are the transects T1 through T10 first as one table. We've got a thal wag, and you record the height, at the thal wag. And then wherever I've set up my station, I'm going to record the match point height that I'm using for that transect. So for in this example here, T1 and T2 we're using setup 1. So I would record a value of 6.5. So you come here, you type 6.5 in the match point cell and 6.5. But then for T3, now I'm going to do 4.5. So I would put 4.5 for T3 and T4 and so on. So you write those match point heights. We know that we're never going to skip a match point. Like it's always going to be from setup to setup. Some number of transects are at one setup, then another. We're never going to skip a match point. It doesn't work that way. So you need to do all of the cross-channel code locations, all your key points have to be done from the same setup. So if you can't see all the points in a cross section from a setup, that's not a good setup. Okay. So that's how we've set this up. So you write the match point, you write the height at the thal wag. Now, for each other location, you would measure the height value where the H is, and then D is a distance. So if I come over here, if I have a thalwag in the middle, from the thalwag, I have to measure the distance from the thalwag to every other point, and it's always to the thalwag. Like the thalwag is the origin of our lateral measurement. So we have a streamwise measurement, which is distance downstream. That's uniform for the T cross sections. We don't have to worry about that. But the distances for our lateral distances, we can use that using the rangefinder. If somebody stands at the thalwag, another person can go to all the other points and shoot the distances. And you would just, of course, you're going to record what are your codes, but you're always going to have a left riverbed toe and a right riverbed toe. Let's say you have an active channel top, T1 terrace top, I don't know, VFE, whatever you have. You could just go across this cross section. I'd get all my distances first, and then use the auto level to measure all of your heights. You cannot use the auto level to measure the distances because the auto level is not on the transect, just measuring distances. We're not going to use that as a procedure. And we're not going to get into horizontal angles and all that kind of stuff. We're just going to measure it with the rangefinder or tape measure. So that's this table. If you have more codes that then fit on here, use extra pieces of paper. On the paper, there's also another table that has the other cross sections, the widest, narrowest, and then I just put pull 1, riffle 1, pull 2, riffle 2, pull 3, riffle 3. If you don't have those, you don't need them, or you can just continue using the piece of paper for T1, T2, and so on. And it's the same thing with your match points and notice over. However, these cross sections are not on an equal interval. If I go all the way, I got to go way back, way back to here. Oh, that was it here. Okay. So for example, I have a pull cross section between T6 and T7. For the auto level, I have to know how far downstream from T6 the pull cross section is. So I have to know that it's downstream of T6 and then how far it is. Or for the riffle, I have to know that it's after T8 and then how far down. So if I go all the way back to where we were, blah, 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 here. So that's why I have these two rows above it. It's like, what is the cross section upstream of the W cross section? So write T1 or T5. And then what is the distance from that cross section to the W cross section or to the N cross section? And you just have to write down that distance. From that, we can work everything else out. And then otherwise, it's the same. Just give me the height of the thalwag, your match point heights, and then your distances across the transect from the thalwag and your heights. Okay, well, by now, I hope you've taken a lot of breaks because I wish I had taken a break. I feel like I need to go to bed. And speaking of beds, we got to do the riverbed sediment characterization. Oh my gosh. And photo documentation. This is we're very near the end. So for riverbed characterization, we will be doing something called a pebble count. I'll describe the procedure and then illustrate it. We're going to do a pebble count only at every T transect. We're not doing them at P, R, W, and N ones. We're going to observe 8 particles per transect, and we'd like them to be roughly spaced across the cross section. They don't have to be perfectly equally spaced, but roughly equally spaced across it. So how does that work? So first, if it's assuming it's weightable, walk across the transect to see if there's any hazards on the ground or on the bed, like glass. You don't want to reach down and cut yourself. You don't want to puncture yourself with a medical needle. If there's anything like that, follow the safety procedure, which is all written out. We have puncture and cut resistant gloves that you could wear. You can't pick up a sand grain with it, but you can pick up gravel and cobble with it. So there's going to be some safety issues to be mindful of. In any case, evaluate the safety. Also, while you're walking across, count your steps. And it doesn't matter how big your foot is, just count your steps. Um, and get your width, divide it by 7 to get 8 equidistant spaces. So if I have, let's say 35 steps, then divide it by 7, it's five steps per site. So I start at one bank, and what do? You we did that already. Okay, you lower your pinky finger off to the side where you can't see it. La la la, look up, put my finger down, and hit the bed. Whatever grain I touch, I want to do my best to pick up that grain. The danger is, here's my grain. When you have a big grain like this Big Mac here, or whatever this sandwich is, then I should have. I'm causing trouble. Okay. Oh, I'm getting a little wonky. Okay. You hit a grain, fine. You hit the grain, pick up the grain, measure it with the gravel template. Now, what the problem is that if you have two of these bigger grains, do I have another big grain? I don't know. You have two bigger grains. I'm struggling here, but oh, hey, it's like blurting it out. You have two bigger grains. When you put your finger down, it's very hard to like go in the hole between two bigger grains. But if you do, try your best to go in that hole and get whatever the smaller thing is that's in there. If you hit a grain and it's like totally buried, yeah, you got to try to wiggle that thing out and get it. Okay, so get your grain, pick it up, and put it through the particle size of the template and record the smallest hole it can fit through. If the grain is too big to pick up, like it's a boulder, or it's just a cobble and you're not that strong, then you go on to plan B shown below. Okay, so what is a gravelometer? A gravelometer is a piece of metal that squares have been stamped out of. Why don't we just use a ruler, Greg? The reason is because scientific studies have been done that show that if I have a grain, it's very, very hard to take a ruler and measure it correctly. And if you take 100 grains off a river and you bring them back to the lab and you give 10 people and you have them measure 100 grains, guess what? You get very different results because the grains are all weird shapes and sizes. So they invented this really cool thing called the gravelometer or gravel template. You just you turn it around, like you can't jam it. You don't bound this thing in there, but you move it around, you try to get it in. If it goes in, it's in. And so let's say, let's go here. So pick up one grain at your pinky. Now, the smallest hole here is 2 millimeters, which is the transition from sand to gravel. I mean, if you look at the ground and it's all mud, it's mud. Tally it as 2 meters, but still you go across and you're going to make 8 tally marks, like 1, 2, 3, 4, then across that, like tallying style. And yeah, if it's all mud or fine sand, it's all less than 2 millimeters. It is what it is. You don't even have to try to pick it up. If it's bigger than 2 millimeters, do your best to pick it up and try to shove it through there and see what you get. On the other hand, if something is bigger than 1 meter, it's a giant boulder. We're not measuring it. We're just tallying it as bigger than 1 meter. If it's bigger than the biggest square, which is 180 millimeters, you see the 180, then you can use the ruler along the side. There's a 300 millimeter ruler there. Well, you're only going to use that if it's between 180 and 300. Then you can use the edge ruler. In that case, you want to measure what's called the B axis. So the longest, like if I take my phone, if I orient it vertically, I can go through a hole. If I go like this, I can't go through a hole. But what matters is the intermediate or B axis. That's what's going to determine the size of the hole that it can fit through. So that's why you want to try with a ruler on the side. Again, it's not going to be super accurate, but you do what you can. If it's less than 180, start putting it through the holes. If it's between 300 and if it's between 300 and 1 meter, you could use a tape measure to measure the b-axis. If it's like half embedded in the ground, just check the box between 300 to 1,000. We just need to put it into the right box on the tally sheet. Yeah, if it's between 2 and 180, go ahead and stick it through the holes. Again, tally the smallest hole. So let's say it does fit through 64 and it doesn't fit through 45. I want you to tally it as a 64. Why? It doesn't matter. Only matters that you be consistent. I just need to know I'm between 45 and 64. That's what I need to know. In this study, we're going to do the same method as the statewide procedure, which is you tally the biggest thing it did fit through. The smallest thing it did fit through, which would be 64. It does not fit through 45. We're going to tally it as 64 and then move on. All the sheets will be the same. It'll all work the same way. This is what the data sheet looks like for the gravelometer. On the left is a size class. So yeah, we don't have to, if it's between 300 and a meter, you just have to know that it was smaller than a meter and it was bigger than 300. And then it just goes into that category. Yes, 180 to 300. So if it fit in the 180, but it doesn't fit in the 128, it's going to tally as a 180. So for each of the transects, there will eventually be 8 marks somewhere along here, 1 mark for every grain that you measure. So you just tally the number per class, 8 per transect, and note it as the smallest hole it can fit through. And we just do that. So 8 times 10 means we're doing 80 particles per site, which is a reasonable number to characterize the statistics for grain size of the site. All right, the last slide. After the first person finishes their work, if nobody else needs any help, they should walk around the outer edge of the site, get some good photos of the site from higher vantage points. We never have enough good photos to understand the sites later. Yay, we made it. Okay. So, wow. So what can I say? What I can say is I've used up a lot of your time. I hope you watch this at like faster speed. But remember, everything I've just described gets us 1 box out of all these boxes. It gets us 1 box. But that box is so important. It's the field data. It needed to do everything else below it. Without that box, everything fails. So that's why we put all this effort in. I'm sorry this was a long presentation. I hope you took some breaks, and I hope I'm funny to look at. Okay, bye-bye. Thank you very much.